So welcome back. Welcome to another Thursday GG128 Engineering Calculus 2 video. And the last video we introduced the concept of the area problem, and we're looking for how we're going to solve the area problem. And we said that okay, we're going to use rectangles to approximate it. Essentially, we're going to use stripes to approximate the area, right? Because we looked at it that fundamentally the issue with us uh, not using our length times breadth thing was the fact that the height of the curve is constantly changing. So the height of the curve is constantly changing. So we assume that why don't we look for an interval on the x-axis where the height is just constant? So for instance, if we are starting, let me again erase from somewhere like here. Let's just make it arbitrary. You can start from 0, but I just don't want it to be from 0, so I won't always be thinking it's from 0 to somewhere. I just take it from here to here, and let's have it be. So I saying, okay, our issue is the height is changing. So can we break down the interval on the x-axis such that the height where the height just stays constant? So like for instance, if I can say that okay, between let me take this top point, I can say that at this point the interval of that point, if we can say the height is constant there, I can draw a stripe down. Okay, I can draw a stripe down, note note where it is on the x-axis, or what that width is going to be, that tiny width is going to be, multiplied by the height we have here, and that will be the area of that single strip. Then if we can do it for every other place, it's going to be rigorous obviously, but if we can do it for every other place where the height, it points where the height, the intervals of the height being the same. So since the height is changing, but we know that at any given point it has a particular height, so we know that for a particular small interval it's going to have the same height. So that small interval is what we are going to try and trace down to the x-axis, which is what we're calling the width of the rectangle. Then the height is the function as it corresponds at that point, that constant height. Okay, and that's what we said we're going to do. But we said that since that is so rigorous, and instead what we're just going to work with at first is going to be an approximation. So we're going to use an approximation of using rectangles. So, but the concept will still have to remain. Remember, the only way we know how to get the area is when the height is constant. So we are going to make rectangles, and for you to have rectangles, obviously the height has to stay constant. So we are going to assume we're going to break down this this curve into intervals such that we are going to assume that between the intervals that we've broken it down into, the height is constant during those intervals. So this is what I mean. So if we come over here and let's call it, we're going to break it down into intervals. So our first point in the interval is going to be A, which we're going to call x sub naught now. And I can have, let's say, x sub 1, x sub 2, x sub 3, x sub 4, x sub 5. Okay, I should have made it, and let here just be x sub 6. What we're saying is that between x0 and x1, we're going to draw a rectangle. So we already know the base. The base is going to be, let me use a different color so that it stands out. And what do I choose? Okay, let me just go yellow. Can't go wrong with yellow, right? Okay, so we already know what the base is going to be. But what is the height going to be? That is the issue. What is the height going to be? It could either be the height of the function at the left endpoint, at the left interval, that is at the x0, or it could be the height of the curve at this right endpoint, or that is the height of the curve at x1. Again, with between x1 and x2, we already know the base. The base is between x1 and x2. But what would be the height of the curve? It could be the height of the curve at x1, because remember it has to stay constant. We have to choose one, because we said that the concept behind our approximation is that between the interval we've chosen, the height stays constant. Remember, but since we know that we are going to have that so much, if we want to make it so accurate, but we're just having an approximation here, so we are just assuming to get the approximation that between the interval we've chosen, the height is constant. But we know that as we're saying it is not the case. So we have to pick. Which one do we choose? So the point I will pick, because here it could either be the left, or it could like I said, it could either be the function at the left endpoint. That is, here is x. The left endpoint here will be between x sub 0 and x sub 1. The left endpoint is x sub 0 and the right endpoint is x sub 1. So it could either be the function at x sub 0, or it could be the function, let's just track it here, or it could be the function at x sub 1. But we're not allowed to have something like this. Okay, we're not allowed to have something like this. Can you see? Instead, it must be a rectangle, like we said. So what do we do? Depending on which one we choose is what defines the kind of approximation we're doing. So like I mentioned, we have what we call left endpoints and right endpoints. So left endpoint and right endpoint. So from the name, you can already guess what this means. It means that if we're using left endpoint, it means that between the interval of our rectangle, the function, right, or the height of the rectangle will correspond to the function at the left hand side. We're going to denote it by xi minus 1. The reason why I'm doing this by xi minus 1 is I'm assuming that xi is our function here. So the one we're taking is xi minus 1. So I'm imagining that the interval for each rectangle is giving us xi. I'm saying the interval of each rectangle is giving us xi minus 1 xi. So our x naught, x1, xi minus 1 xi. Okay, so it means that our function is being taken, or the height of the rectangle is going to be equal to xi minus 1. So what do we mean here? It means that, for example, with this problem, if we're taking the left endpoint, it means that the height between x0 and x1 is going to be equal to this. It's going to just correspond to the height at x0. Between x1 and x2 is going to be equal to the height, right, which is the function at x1. So it's going to be equal to the height. So between here and here, we're going to have a constant height from x1 to x sub 2. Then between x sub 2 and x sub 3, we're going to take the height at x sub 2. So we're going to have something like this. And then this, where we have, I can draw my x sub 3. Let me then change this up. So we have this, x sub 3. It even allows me to straighten things out. So I can call here my x sub 4 and x sub 5. Okay, so let's return to the problem. So what we can have is that between x3 and x4 is going to be the height of the function at x sub 3, which is here. So to be constant to x sub 4. Then between x sub 4 and x sub 5 is going to be the value of the function at the height of the rectangle between these two. It's going to equal the height of the function at x sub 4. Then between x sub 5 and this last one, which I'll call x sub 6, since I called this one x sub 0, is going to be equal to the height at x5, which is 0. So it's just going to be a rectangle with 0 height. Okay, so what I can say then is that my rectangle for the left endpoint is what we're dealing with now. For the left endpoint, I can say that the area is equal to x naught minus x1 minus x naught multiplied by the function, which is the height, which is the function at x sub naught, plus x2 minus x1 multiplied by the function at x sub 1, plus x3 minus x2 multiplied by the function at x sub 2, then plus x4 minus x3 multiplied by the function at x sub 3, then plus x5 minus x4 multiplied by the function at x sub 4, plus x6 minus x5 multiplied by the function at x sub 5. So what we can just notice that when we're dealing with left endpoints, we're starting from the function that we're taking is going to always start from x sub 0, because between the first two intervals x sub naught and x sub 1, the function, the height will always be equal to the function at x sub 0. And this is what the area will be approximately equal to. We know it's not exactly equal to it because we can see that there are some places that are not accounted for. So for instance, we have here not being accounted for, we have here not being accounted for, you have an overestimation here, an overestimation here, an overestimation here, and an underestimation here. So we can tell that, yeah, it's roughly, yeah, not very good though. And, and that becomes an issue. But we can say it's just an approximation. Well, if we want to simplify this approximation here, we can say that, okay, it would be best. We notice that we're having this x1 minus x naught, x2 minus x1, x3 minus x2, and that we always have to compute. So since this x1 minus x2, these subtractions that we have here correspond to the width of the rectangles, would it not be better if they can all just be the same thing? If we can make it, if we can space it out evenly, it means that we will drop our problem down significantly. So because it means we just have to calculate the delta x. So we can say if here's delta x, 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 here's delta x. So I can say delta x now, and to factor everything out, it will be x sub 0 plus x sub 1 plus x sub 2 plus x sub 3 plus x sub 4. So x at 4, not sub, x5, and this is what we have as our answer. We've broken out the problem significantly, just reduce this, and we have something like this. So for the left endpoint, this is what we have, right? And obviously, if it means that if we are going to space them out evenly, it means it's just simple arithmetic, right? So what will delta x be? If we want to make sure that the rectangles all have equal width, it means that we have to divide them, the gap between the space between the intervals a and b evenly. So it's going to be b minus a all over n, where n represents the number of rectangles we're using. And speaking of the number of rectangles, what you can tell from here is that, okay, if we want a better approximation, we just increase the number of rectangles. Why? Why, do? If think about it for a moment. Why is it that I said if we want better approximation, we increase the number of rectangles? The reason for that is because if we increase the number of rectangles, it means that we have, and if we increase the number of rectangles, and we still want this evenly spaced thing, what this means is if our n is going up, it means our dx is going down, right? Inverse relationship between dx and n. And what happens when the x becomes smaller? It means that our rectangles are having smaller and smaller width. And if we're having smaller and smaller width, what happens? If we're having smaller and smaller width, it means the approximation becomes better. Remember, we said that the concept of our approximation is that we imagine that between the two intervals we're using, the value of the function stays constant. That is, the height is constant. Since we know the curve is constantly changing, and we could see that it's the way we have them being constant is only at very tiny small intervals because the curve is constantly changing. So if our delta x is very small, we have better results. And sorry if I squeeze your ears. Sorry, just trying to lay emphasis there. And since we want our delta x to be small, it just means that our n is becoming large. So the more rectangles you have, the better your approximation is going to be. And you can test this out for a lot of things, as we're going to do going forward. But for the time being, so I think one might ask, okay, so it means that if we have an infinite number of rectangles, doesn't mean we get the, the exact answer? I'll think about that for a moment. But that idea will be very fundamental going forward. But with this now, so this is the left endpoint. This is what we have for the left endpoint, that we can say approximate the area is equal to the delta x multiplied by the function at x sub 0 plus the function at x sub 1 up until, actually I'll just let it go up until x sub n minus 1, yes? N minus 1. Oh, sorry, it should be xn minus 1. Xn minus 1. I should not have been writing 1, 2. This one, so I'm writing inside is x sub 1, x sub 2. Okay, no wonder I was saying x sub when I was saying that. So x sub n minus 1. Because from here, the heights we took were from x sub 0 to x sub 5, right? And we had 6 rectangles. Remember, this one is still a rectangle just with 0 height. So this is what we have here. Okay, so it means that we'll always be going from x sub 0 ending at xn minus 1. So what about the right endpoint? What about the right endpoint? How are we going to deal with that? Let me increase the size of this so quickly look at that. From the right endpoints, well, from what we described before, it just means that when we are going over when we're choosing the height, we're going to choose the height of the function that corresponds to the right interval. So for instance, between 0, x sub 0 and x sub 1, the height of the rectangle will now correspond to the height of the function when at x sub 1. So let's do that quickly. Let me see if we can make this neat. I doubt it. Let's see. Okay, let's just do this. Okay, not too bad, but let's work with this. We're still going to be using the same interval, so we don't mind this part still staying the same. So let's, the width is going to stay constant, remember, but the only thing is what the height is going to be. So between x0 and x1, the height of the rectangle between x0 and x1 is going to correspond to the height at x1. So this is what we're going to have. It's going to be something like this. So it's going to be the same. Let me erase this. So it's going to be the height at x1. Between x1 and x2, the height we're going to take is going to be the height at x2. So this is what we're going to have. Okay. Between x2 and x3, the height we're going to take, I think this was poorly done, but let's just work with it. This is our x2. This is our x3. So the height we're going to take is going to be the value of x3, the one at x3, not the one at x2 anymore. So between x2 and x3, the height of the rectangle is going to correspond to the value of the function at x sub 3. The one at x sub 3 is x sub 4. We're going to take the one at x sub 4. Between x sub 4 and x sub 5, we're going to take the one at x sub 5, which is 0. Between x sub 5 and x sub 6, we're going to take the one at x sub 6, which is this. So this is what we'll have here by using the right endpoint. And it's quite interesting, isn't it? We have a different diagram, but see the same kind of approximation we're dealing with, just taking the left or the right. And here we can tell that again it's still an approximation, and we can tell that because here is an overestimation, here's an overestimation, here's an underestimation. It's not counting for these places, and overestimation here as well. So we know it's not still accurate. So let's like what we did with the left endpoint, let's write out what this is approximately equal to. What this would be is x1 minus x0 multiplied by the function at x1 plus x sub x sorry, x2 minus x1. Let me quickly go over this. X minus x1, f of x2 plus x3 minus x2 at f of x3 plus f x sub 4 minus x sub 3, f of x4 plus x5 minus x4, f5 plus f of x of 6 minus x, sorry, not f. Why did I just, like, I do not like autonomous things. Okay, so this is what we should have. 5 multiplied by f of 6. So this is what we have here, and this is what we said the area is going to be equal to. And like what we did with our left endpoint, we want it to be, to simplify this. So the best way to do that is to make sure that all of these ones are, the width are all of the same length. So we're going to call that uniform with the x. So it's just reduced to f of x sub 1, f of x sub 2, f of x sub 3 plus f of x sub 4. And if I want to make it general, plus all the way up to f of x n. Okay, f of x n. And this is what I have here. Okay. So this is what we have here. We'll work on the notation a bit. So we have x sub f of x sub n. Okay, so this is what we have right here. So, and obviously again, if they're uniform, it means that our delta x is also equal to this. So b minus a. And again, our approximation will be better if our n is increases. Okay, so this is what we have here, and we can see that this is a very funny way of writing. It takes a lot of space, and it's not very, we've done a good job reducing the the algebraic representation of the area, but we want to go further. We want to see a better way of representing this area sum that we have, and that's what we're going to come up with now. And that's what will lead us to what we call the Riemann sum. a compact way of representing what we've just said here, you through the use of sigma notation. Let's see what that is all about, and we'll be looking at that in the next video.